So here we're shown a setup where a radioactive source is being measured for its activity by a detector, and we have a graph that shows source A and source B, so two different sources, and shows how the activity measured in counts per minute is changing as that source is then moved a distance away from the detector. So we've got two lines, one for source A and source B. So we're then asked how the graph shows that source A only emits alpha radiation. Now, if you look at the line for source A, you can see that at about 3 centimeters, the level of radiation being detected drops really significantly, and it drops to a level that it stays at for the rest of the time. Now, the fact is that level it's dropped to is what we call background radiation. So if you remember, that's the low level radiation in the background from natural sources that surround us all of the time. So there's no change in the amount of radiation being detected when the detector is actually moved. And that's how we know that this must be alpha radiation, because alpha is the radiation that will travel the least distance in air. It's also the least penetrating. Okay, so we know that the radiation from A only travels 3 centimeters before the rate drops significantly. And when it drops to background rate at that point. And the reason, therefore, we can link that to alpha is because alpha has the shortest range in air. So now we can't tell from the graph what type of radiation source B does actually emit. So we know it's not alpha because it does travel a greater distance, but we can't use the graph to tell us whether it emits beta or gamma. So we need to explain how an absorbing material could be used to show which type of radiation is emitted by source B. So now we have to think about what we need to stop beta. And what happens is beta is the one that requires aluminium to stop it. So if we were to use an aluminium sheet, then what we would find is that the beta radiation wouldn't pass through that, but gamma would. So remember, gamma is the most penetrating and requires lead to stop it. So beta radiation wouldn't pass through an aluminium sheet, but gamma would. Okay, the teacher took safety precautions during the experiment. Suggest one safety precaution the teacher would have taken to reduce the radiation dose the teacher received. So this is where I want to introduce you to the TARDIS will save mankind. And this little phrase, silly though it is, will help you remember how you can protect yourself from radiation and how radiation can be dangerous. So TARDIS, the three things that you can do to protect yourself is time, it is distance, and it is shielding. And then mankind, the reasons why radiation can be dangerous: because it can mutate, it can kill, and it can damage. So if you remember the TARDIS will save mankind, that is a little phrase to help you remember what you need to do in terms of protecting yourself from radiation. So if we use this in this question here, then we can talk about increasing the distance. We can talk about limiting the exposure time. We can refer to shielding, so in terms of not touching it, so using tongs or forceps or something to hold the source. And then shielding wise, we can wear a lead apron because we know that lead will stop the radiation from penetrating. We can use a safety screen. We can keep the source in its box, more shielding, and we can also point the source away. So quite a few things you can say there, any one of those to get the mark. Suggest one safety precaution the teacher would have taken to avoid being contaminated. So contamination is where the material actually becomes radioactive as a result. So we are looking for ways to limit the teacher becoming contaminated with radiation. So that is making sure they don't come into contact with the source at all. So that is things like wearing gloves or an apron, wearing a lab coat, and again using the tongs or the forceps so that you don't actually touch the material. So anything that prevents the teacher from actually coming into contact, because that's when you get contamination happening. Here we are shown the number of atoms in a radioactive element in a sample and how that number of atoms varies with time. We talk about the activity is the rate at which a source of nuclei decay. So rate means how quickly. Determine the activity of the radioactive sample at 300 seconds. So if something is the rate, we're looking at how that changes with time. So what this means is on our y-axis we've got number of atoms, and on our x-axis we've got time. So actually if we take the number of atoms and divide it by time, that is the activity, because that is the atoms per second that we've actually got. So what that means is we need to do a gradient because we want the change in y divided by the change in x. But you can see this is a curve. So what that means is we are going to need to draw a tangent. So a tangent is a straight line that roughly grazes the graph at the point that we are interested in. So you'll get 1 mark here for drawing the tangent. Now you want to find the gradient of that tangent. So the gradient is your change in y divided by your change in x. So when we do that then, our change in y, we can see is 3.5 minus 1.5, but don't forget that is times 10 to the 23, look at the scale. And then our change in x, we have got 450 minus 200. So that gives us 2 times 10 to the 23 divided by 250. And that gives us a value of 8 times 10 to the 20. And the final mark is for the unit, and we measure activity in becquerels.